Hello friends, welcome back to our channel. This is part 2 of the video series where we are going to discuss CAM memory in detail. In this video series we are going to discuss what is a CAM memory, how to design it, what are its applications, and I will show you the digital design of one of the application as I promised. And now without wasting much time, let us get started and continue where we left in part 1. Friends, in part 1 we discussed what is CAM memory and how it is different from RAM memory, and we saw the basic pinout of CAM memory and RAM memory. We also discussed TCAM, that is ternary content addressable memory, and we saw that how it helps in partial matching. Friends, if any one of you have not watched that video, please watch it, then only you will be able to enjoy part 2. Friends, in part 1 I left one question unanswered, and the question was, it is okay that CAM can compare the input data with all of its memory locations, and if it matches with any of the memory location, it will give the address of that memory location and match flag will be asserted. But the question was, how do we fill this CAM memory? Then I told you that in this PDF, whatever pinout is shown, it is very limited one. It is not complete. So now in this video, I am going to show you the complete pinout of CAM, and there only I will explain how we fill the CAM memory. Friends, to demonstrate the complete pinout of CAM memory, I am taking help of one of the another document from Xilinx. It is on parameterizable content addressable memory application note. XAPP 1151. You can search it on Google, it is readily available. Friend, this is the complete pinout of CAM memory. Let me zoom this area. Input side, we have two types of buses. One is which is responsible to write inside the CAM memory. Another interface we already discussed, which is to compare. And at the output side, we get the match address, we already discussed, match flag we discussed. Apart from that, it has multiple match and single match, two other flags we will discuss. Two auxiliary outputs, busy and read warning. We will see these two flags also, but most probably these two flags are specific to Xilinx implementation. Friends, as you can clearly see that there is a data mask bus which is used to mask some of the bits of the data input bus while writing it into the CAM memory. Similarly, we have another mask bus, that is CMP data mask bus. We already discussed it in detail in our part 1. But just for your knowledge, I am telling you that these two buses are optional buses. If you left them unconnected or you tie them to the zero value, the same CAM will act as a normal CAM which can only compare zeros and ones. But if you start using these two buses, data mask bus and CMP data mask bus, then the same CAM can act like a TCAM. Now let us try to study the interface which is used to write data inside the CAM memory. This is the input data bus, this is the write address and data mask bus. These three buses are required to write data into the CAM memory. Now firstly we will discuss a simple mode, we will not discuss a ternary mode. In that case we can keep this unconnected or we can tie it to zero values. So this is not useful in that case, in normal mode. Then in that case we are left with only two buses, write address and data input bus. Data input bus carries the data which we want to write into the CAM locations. And write address indicates the address where we are going to write this data carried by data input bus. Friends, apart from address and data bus, there are other two signals, enable and write enable. So enable is very important to enable this CAM memory either for write operation or comparison purpose. And write enable is important when we are writing data into the CAM memory. Friends, now let us discuss that how we write CAM memory in a ternary mode. In that case, data mask bus will come into the picture. First thing I want to make it clear that the width of data mask bus is equal to the width of data input bus. As we already discussed that if all the bits are 0, then every bit on a data input bus will be written inside the CAM locations. But if any of the bit inside the data mask bus is high, corresponding bits in the data input bus will be masked and those bits will not be written inside the CAM locations. In a nutshell, for that particular location of a CAM memory where we have masked some of the bits with the help of data mask bus, the content of the masked bits inside the CAM location will be don't care because we have not written. It can be either 0 or 1. Let me try to show it graphically. Friends, in part 1 we discussed compare data input bus, compare data mask bus in detail. And now let us see the remaining signals. Friends, as we already discussed CMP data input, CMP data mask signal, I am removing them for the time being. The remaining buses data input, write address, data mask. This interface is used to write data into the CAM memory and we have already discussed in detail about all these signals. But now I will show you practically how we write data into the CAM memory. Let us say on the data input bus I have this data 11001111. Address is 101 as I have total 8 locations inside the CAM memory. So address bus is only 3 bits long. And address is 101. That means 5. 0, 1, 2, 3, 4, 5. It is indicating this CAM location. So this data will write into this CAM location. But some of the bits in the data mask bus are high. LSB2 bits are high. Now when we try to write this data inside the CAM memory, this data mask bus will interact with this data input bus. Now first 2 bits will be written inside the CAM memory. 00 will be written, 11 will be written. Now the 2 LSB bits are masked. So data input cannot write into these 2 locations. So these 2 locations will remain XX. XX means we are not writing into it. There can be some junk data 0 or 1, we don't know. Friends, that is how we write data into the CAM memory. So enable and write enable is clear to you. Now I will discuss the output flags. These are very important. Friends, when we apply compare data input along with compare data mask, this data is compared with each location of the CAM memory. And wherever this data matches, the address of that location will appear at match address. Along with the match address, this match flag will be asserted. When match flag is asserted, it means that the content on the input data bus is matched with one of the memory location inside the CAM memory. This is very important to note that matched indicates that at least one of the CAM memory location matches with the input data applied. Along with that, if single match flag is asserted, that means the content on the data input bus matched with only one location inside the CAM memory. But if multiple underscore match flag is asserted, that means that the input content matched with multiple locations of the CAM memory. But friends, one obvious question arises in our mind that if multiple match flag is asserted, that means the input data matched with multiple locations. Then which address will appear at the match address? In Xilinx CAM memory, friends, at the time of compilation, there is one parameter which decides which address should appear at the match address. But there are only 2 options. Either lower matching address can appear or highest matching address can appear. That is governed by the parameter. Friends, with this, I gave you the complete pinout of CAM and TCAM, and I also explained that how data is written inside the CAM memory. So only these 2 things were promised in our part 1. So both the options are covered. Now what about part 3? In part 3 we will discuss how can we design a CAM memory. Friends, with this I am going to end this video. I hope that it will be informative and interesting for all of you. If you also like this video, please press the like button and you can share your feedback as well. And in future also we are going to create many such videos. So to be aligned with our channel, Don't forget to subscribe it and press the bell icon to get the notification of all the upcoming videos. Thank you so much for watching and your time.